This is How to Math with Dr. Ian Lundholm. In today's episode, orthogonality. So this is section 5.3 in our text, and we've already encountered a lot of these ideas recently with regards to the dot product and projections, orthogonality, all that good stuff. So some of this we are going to skip through quickly, and other parts are definitely worth some thought. Here we have the dot product defined and the length of a vector. We're good there. Some properties of the dot product. I believe that we've already attended to all of these. Commutative, distributive property, we're good. Yep. Moving on. This is what it looks like to find the length, the squared length of x plus y. And I guess I will notate this a little bit. So yeah, we're taking the dot product of the sum of two vectors. Dot product with itself. And you can see the result here is literally the same thing as the law of cosines. Remember that the dot product between x plus y, x dot with y, that is the length of x times the length of y times the cosine of the angle in between them. And so, yeah, this whole thing is 2 times that. So this is literally the law of cosines just written in vector form. Cool? Moving on. All right, here we have a set of vectors, f1 through fk, and these vectors span an n-dimensional space. So we know that we have at least n vectors in this set. Furthermore, suppose there exists a vector x in Rn that is orthogonal to all of these vectors. This seems impossible unless the vector is the zero vector, which I think ends up being the case here. Yes. So all this is saying is if you have a spanning set for a space, and then you have a vector that's orthogonal to all of the vectors in that spanning set, that vector has to be the zero vector. There's no way that you can create another linearly independent vector from a set that already spans the space. That makes sense. We've already got all of our dimensions filled there. Cool. All right, now we'll look at the Cauchy inequality. Here we've got the absolute value of x dot with y is less than the product, or less than or equal to the product of the length of x times the length of y. There is going to be a long explanation here from our text that uses properties of the dot product and all that good stuff to actually figure this out using a quadratic, and it's pretty long and involved. I think the way that would be most insightful to actually think about this problem is to realize, again, that this dot product, x times y, when we're looking at the absolute value of that, we're looking at the absolute value of the length of x times the length of y times the cosine of the angle in between them. And so literally what we have here is the length of x times, and I'll put double things because they're using double things for the magnitude here. The length of x times the length of y times the absolute value of the cosine of the angle in between them. And you can see here that, this part's exactly the same And the only thing that's different is this cosine part, and the absolute value of the cosine of theta is only 1 when, those vectors are pointed in exactly the same direction or exactly the opposite direction, meaning that they would be linearly dependent. So that's probably the easier way for me to think about the Cauchy inequality. This quadratic stuff's not bad, but it's just long. See? Told you it was long. There's a whole nother slide here. But this is, done very formally, rigorously. It's good. Deserves its place in math. Anyways. Here we go. Triangle inequality. That's somewhat similar to the Cauchy inequality, except this time, we're not multiplying, we're adding. And literally, this is just based on the legs of a triangle, where the third leg of a triangle can't be longer than the sum of the first two legs. That's really all this is saying. Please. Distance between x and y, totally, we've done this. Great. We can find the distance between things. Cool. Orthogonal set, and orthonormal. Again, this is some vocabulary that we've already discussed. Orthogonal means that you're perpendicular. It means that the dot product between two vectors is 0. An orthogonal set is a set of vectors where everything is orthogonal to one another and none of the vectors are the 0 vector. And an orthonormal set is an orthogonal set that is only made up of unit vectors. So, yeah. It's weird in our text that we use normal in two different ways. I just want to make this explicit. The first way that we experienced the word normal was for like a normal vector that's pointing in a completely orthogonal direction to a certain plane. So, a given scalar equation for a plane will have an orthogonal vector whose coordinates are the coefficients in that scalar equation for the plane. And we call that thing the normal vector. But that's the first way that we use it, and now we're using normal in a completely different way. We're saying to normalize a vector means that you shrink it down to unit length. And so orthonormal means perpendicular and unit length. A little bit weird. Sorry for the double talk. And there's a tiny bit of subtlety here in this definition. You would not necessarily be able to say that x, y is an orthogonal set if x or y was the 0 vector. That's all that is. That's not that big a deal. Okay, moving on to some examples. Yes, the standard basis is an orthonormal set. That's an orthogonal set, but it's not normal. If you have an orthogonal subset and you scale each of those orthogonal vectors, it's still orthogonal. No big deal there. And yes, if you scale all of those vectors in 2 by 1/2, then you have an orthonormal set. They're all of unit length. Cool? Yes, and this is normalizing an orthogonal set. You're just dividing by the magnitude to make them unit length. No big deal there. Yes, we could verify that this is orthogonal just by taking a bunch of dot products and then normalize it by dividing by the magnitudes. We know how to do this. That's what it looks like in math. Cool. We're going to use that soon. Sure, Pythagorean theorem here. As long as we have, an orthogonal set of vectors, x1 through xk, then their sum works out according to this equation because dot products, lots of dot products. There you go. Let's see. We've got an orthogonal set, then it's independent. I mean, that's really pretty obvious. Again, this is going to be pretty mathy. A normal person wouldn't even think to like prove this necessarily, but in some instances, I mean, it's good to know that this definitely causes things this way. Like, if you have an orthogonal set, it should be independent. It's kind of like duh, but this is what it looks like to use the definition of linear independence and show that, orthogonality implies the condition that, our set of vectors is linearly independent. Cool. Given an arbitrary vector x, it is trivial to express x as a linear combination of the standard basis vectors, because literally all you do is multiply all of the components of x times each standard basis vector. But this is an important pattern to recognize because we're going to utilize the same pattern when we express x maybe as a linear combination of basis vectors that aren't the standard basis. In this case, it's really easy, but soon we're going to get to the meat of this section and get some interesting ideas here. So a problem is if we have an orthogonal basis b that is not the standard basis, and we have an arbitrary vector x, how do we express x as a linear combination of the vectors in B? Our book uses the term Fourier expansion to highlight what's going on here. But basically, what we have is we're given a set of vectors up here that is an orthogonal basis for a subspace U in Rn. So that's the set of vectors. And we want to be able to express this vector x as a linear combination of all of our basis vectors. So we're trying to use, this as the basis of a new coordinate system. And in order to do that, in order to come up with this exact linear combination, what we do is we take a bunch of projections. This part is the projection, well, actually all of it, the projection of x onto F1. And this one's the projection of our arbitrary vector x onto our basis vector F2, and so on. All of those are just a bunch of projections. So yeah, imagine you start off with an arbitrary vector and then you project it down individually onto each one of your basis vectors. And that is exactly how you come up with this linear combination of basis vectors. And I'm going to go a little bit farther so that we can see. All right. Yeah, I'm going to go a little bit farther. I'm going to, highlight some stuff here again. Yeah, this is the Fourier expansion of x, and again, all of those things are just projections. We call those the Fourier coefficients. Do recognize that pretty soon they're going to call this number t sub j, which is like the weight. I don't know why they call I don't know why they use f for the vectors of the basis and t for the actual Fourier coefficient, but yeah, that's what they're doing. So I'm going to say Fourier coefficient, and I mean the letter t, not the letter f. Anyways, here we go. A concrete example. I have this on GeoGebra, so we should be able to look at it in depth. But we're given these three vectors, f1 through f3, and we are, we've already shown that these vectors are orthogonal. So we have an orthogonal basis for R3. These would span the entire space, R3. And we want to express the vector x as a linear combination of our basis vectors. We're trying to use these as a coordinate system. Right now, these vectors f1 through f3 aren't very special, but this will be very handy very soon. Let's say that we were trying to understand how this, transformation was working over time. Maybe we were solving a system of linear differential equations or something. And we wanted to work on this system in terms of using its eigenvectors as a basis for a coordinate system, because eigenvectors are really nice that they don't move around when the transformation is applied. So that's something very stable over time that you could use for a coordinate system. This process would tell you how to represent arbitrary vectors in terms of that new coordinate system that you want to use. So this is a very, useful skill. It's important and powerful. I can at least say that. So we're getting back to this problem. What we're going to do is project x onto all of these basis vectors. So there's a bunch of projection coefficients. These are all the Fourier coefficients. And then this is what the linear combination looks like. Here's what I wanted to do with this. So we have this linear combination, and this weight out front, the Fourier coefficient, these are each going to be, you could think of these as being entries in a vector. Let's write that vector here. 1/3, 3/5, 2/15. I know that's horrible. And you could imagine having these as the columns in a 3x3 matrix. And the result of this multiplication, oh geez, is 1, 1, 1. This vector. And so this is another cool way to think about what's going on here. Right now, the red pieces is what I would call a coordinate vector. Based on, our basis B. A coordinate vector, here let's say, for our basis B. When you multiply that coordinate vector on the left by a matrix full of the basis vectors, and those basis vectors are in B, you do that multiplication, you get the coordinate vector in the standard basis. standard basis coordinate vector. um, so this is a way, doing this matrix multiplication is a way to convert from one coordinate system to another. And a lot of times, maybe you might be more interested in, given a vector in the standard basis, like the one that we were given here, we were given x as 1, 1, 1. What matrix would take you from 1, 1, 1 back to the coordinate vector for our basis B? That would be the inverse of the green matrix that we have here. So if you found the inverse of that green matrix, it would take you from 1, 1, 1 back to the coordinate vector for your basis B. I think that's really cool. It gives us a way to, translate in and out of different coordinate systems. And again, that's a really useful skill. Real quick, let's take a look at, what this is in terms of, visualizing. So we're going to come to GeoGebra here. Just to orient you to what I have, we've got 3 vectors, F1, F2, and F3. Those are the red, green, and blue vectors respectively. And the problem here is given a vector x, and our vector x is the black one in the middle, notice that vector x is at the, it's at the point 1, 1, 1, according to the standard basis, the coordinate system that you see here. But in terms of the coordinate system where we use f as the basis for a coordinate system, so we're using, F1 and F2 and F3, I put in the coefficients, over here for T1, T2, and T3 that we figured out using projections. And this is what it looks like to translate between the two coordinate systems. So this first pink vector, this first pink vector U there, that is the one, that shoots in the same direction as F1. The next one shoots in the direction of F2, and the last one shoots in the direction of F3. And that's how we use that as a coordinate system to locate ourselves at that point in space, 1, 1, 1, according to the standard basis. Cool. This is, available to you if you look in our GeoGebra demonstrations, if you want to check it out anymore. Okay, so what did we learn here? I guess we've learned more today about coordinate systems and using a given orthogonal basis as a coordinate system and locating a given vector in the standard basis within your basis. It's pretty cool. Let's see if there's anything else. Here we go. Again, this is just proof that the Fourier expansion actually gives you what you want. We're using, properties of the dot product again here. But yeah, the projection is exactly what you want to determine these Fourier coefficients. It is worth noting that the projection formula simplifies quite a bit. I think I mentioned this earlier in the projections lecture, but yeah. If you are working with an orthonormal basis, you don't have to worry about dividing by the magnitude. And then here's just another example where we're given four basis vectors and we want to express this ABCD vector as a linear combination of the four basis vectors that we're given. We need to start out by taking some dot products. I guess, that's just verifying that our given basis is an orthogonal set. But, they're saying the Fourier expansion theorem here. Remember that these are just projections. So, on the top here of this first Fourier coefficient, we've got a plus b. That's because we are taking the dot product of x and f1. So f1 and x here. And that's just a plus b because you've got, a times 1 plus b times 1. So yeah, that's x times f1. This is x times f2, x dot f2, and x dot f4 over here. Let's get that out of the way. So yeah, that's just a bunch of projections. The length of all of these vectors is the square root of 2, and so the length squared is 2. That's why we see 2 in the denominators there. But yeah, I guess that's just another example of, expressing an arbitrary vector as a linear combination of basis vectors. So that's all for this section. I do plan on introducing some stuff in 8.1 soon. So this has been about 30 minutes. Be aware that I'm going to release another video with 8.1 as well. And it should be posted and ready to watch. All right. This has been How to Math with Dr. Ian Lindholm. Remember, you've got online homework to do, particularly in regards to 5.3. You're ready to do it now, and you'll be ready to do the homework associated with 8.1 really, really soon. All right. I'll see you in the next one.